Mm. Okay, so let's get started. Welcome to the course of Digital Integrated Circuit, and this is the very first lecture, Introduction. So, first of all, I want to welcome all of you, and as you know, the course name is Digital Integrated Circuit, in Korean, Digital Jitokero. And here we have a code number of EC4202, and you know this is corresponding to the senior uh, course for undergraduate students. And yes, you have 3 lecture hours, and there is no experiment. This is really theoretical course, and we have 3 credit. And my name is Song Min Hong. I'm currently affiliated with the School of ECS. And let's go. So let me just talk about resources available to you. So presentation material, PowerPoint file actually converted to the PDF will be uploaded this GitHub repository. So why don't you just go to that one together with me, GitHub, then you can find, so this is my ID, and DIC, Digital Integrated Circuit 2023 full semester. Then hopefully you have my repository, and when you visit it, and currently we have only readme.md file and only the first PDF file for lecture 1, but every day I will upload my PDF file so you can download it. So actually what I have done in this slide here is just to click this PDF file and you can download it. Yes, so that is the way I do. So I think that you can also follow same procedure. So also there is another previous repository devoted for 2018 and 19. So if you just change its year to 2019, then you will find an archived repository. So although that is somewhat old one, but maybe you can find some information from that part. And homework submission, so usually I prefer to use this GitHub repository for both for distributing my PDF files and also getting your homework. But in this year I will just take the homework from just LMS system. So have you already received my email, welcoming email from this LMS system? So therefore you can also submit your homework submission to LMS system. Also I have my personal YouTube channel, so it contains a lot of pre-recorded lectures, so you can find many also recorded lectures already done for several years, so please refer to this YouTube channel. And this is a textbook, so we will use this West and Harris book, so quite famous, somewhat old, but I think that this is close to the most updated one. So in this field actually it is difficult to find the most recent textbook, so this is, I think that this is quite a reasonable choice to have this book as a textbook. And evaluation, so in this case, no, this course is purely a theoretical one, so we have a midterm examination as usual and also final examination. They are equally balanced, and also homework has the same weighting factor. Of course, homework, we have many homeworks, and midterm and final examinations are just once, so they are yes. So homework problem is not as valuable as one problem in midterm or final examination, but anyway, there is 30%, 30%, and 30%. And also, I wanted to say that there is attendance. Um, Following our college regulation, there is a one third of two-third rule. So if a student just miss one third or more than one third of their regular lectures, then he or she will fail. But in addition to that, I will just check your attendance and use that one as a 10% with a 10% weighting factor to make a final score. But I hope that we are quite a small group, so therefore maybe all of you will attend this course quite regularly. That is my expectation. So I think that that's all for our welcoming messages. So if you have any question on this stuff, so please let me know. So, yes, so whenever you have any question, then is more than welcome. So please interrupt me anytime if you want to ask me any question. And also, although I speak in English, following the college regulations, so you are free to ask me whatever you want. Okay, so then let's go to our lecture. So today, this is the very first lecture. So maybe in many courses, this first lecture is devoted to the introductory one. But I just wanted to dive into the main scopes like MOS transistor. MOS transistor is actually the basic building block of our modern um, integrated circuit, digital, analog, or whatever. Actually, all of them are made of um, MOS transistor. So it is very important to know about MOS transistors. So please, if you are interested with the history of CMOS technology or some very interesting things, so please refer our textbook, or sometimes you can find also very interesting articles from internet. So I don't want to skip, I want to spend the time on the history. So let me just to go to the MOS transistor. So MOS means that metal oxide semiconductor. So metal oxide and semiconductor. And although we say that MOS transistor, that means that actually field effect transistor. So MOSFET is its full name. Then sometimes we say that just MOS or MOS, whatever. So it has four terminal device. It has four terminals. So what I wanted to say is that was true. Four terminal. There are four terminal. But nowadays, the most advanced one is also can be made of three terminal. Okay, then 4 and 3. What are common and what are is an exception? So here we have four terminals and gate, source, and drain. These are three terminals which are essential, and here we have body, or sometimes called as substrate, and this is the last contact or last terminal. So previously, when we have all the technology, that means that this body terminal or substrate terminal was mandatory, but nowadays it is no longer that case. So this is one thing. I will explain it later about the role of these four terminals one by one. But right now, just think that there are three terminals mostly, and here we have N MOSFET, so-called NP MOSFET. So N MOSFET and P MOSFET, so they are both of them are MOSFET. However, depending on their polarity, they are called as N or P. So if you have already attended the microelectronics course, then you are quite familiar with the concept of N MOSFET and P MOSFET, but I will start from the scratch, so I will explain it later. But anyway, the difference is their polarity. Polarity here means that depending on the voltage applied to your gate, these two devices are behave quite differently. Actually, in an opposite way. And yes, so here we have a certain figure number, and this is just follows our textbook. So if you are interested, please refer to our textbook. But this is just a schematic description about our device structure. Maybe you have seen it quite many times. So let me just think about this one. This one is typically N MOSFET, and I will explain the P MOSFET a few slides later. And for a while, just to concentrate on this N MOSFET. Here we have bulk silicon. Yes. Bulk silicon means that some large amount of certain material. And here, when you say the bulk, how bulky is it? So here, bulk means that typically this thickness is about 600 micrometer. So 600 micrometer is regarded as, in this case, bulk. And what is this depth or this depth? Its depth profile is just a few 10 nanometer or a few 100 nanometer. So please try to make a comparison between 600 micrometer and, for example, 100 nanometer. What is the ratio? The ratio is 6,000. Are you with me? So when we have a silicon wafer, so actually in reality, if you are looking at a wafer, then you feel that that is quite thin. Oh, this is really thin wafer. However, actually our device is just fabricated here, and the ratio between this thickness of our silicon wafer, already very thin, and the depth of our device here is about orders of 1,000. So we are using quite much only the surface of this silicon wafer here. And here we have another length scale. Yes, here the distance between these green regions. So why we have green regions? Because these green regions we have n-type impurities. So here we have also n-type impurities. So are you familiar with the concept of impurities in silicon? So everybody understand the concept of impurities. So impurity here n plus means that since we have silicon, then here, for example, phosphorus can be ionized as a positive ion, then it can provide electrons in it. So if we have a lot of phosphorus atoms inside it, then correspondingly we have a lot of additional electrons provided from our phosphorus atoms. So here green regions means that where we have many excessive electrons here. And the distance between these two green regions is quite important, and this is already about nowadays 10 nanometer scale. So now you understand when we visualize our device as this way, if we are really in scale, then not in this way, our drawing should be written like this. This is similar scale and similar scale, orders of 10 nanometer, and here we have a somewhat long and tall uh, figure to describe our schematic. Okay, so anyway, now you understand this is really tiny and surface oriented one was attached to only to the surface area, and now we have a very short distance between this green line and green regions and another green regions. And since we have many electrons, and here we have many electrons in terms of conductivity. Oh, this green line is quite good. It has a high conductivity. Also, this part is quite highly conductive. But how about this part? This part, we have a relatively low number of electrons in it. So when we just count a number of electrons here, then many, almost no, nothing, and many. So this is like this. If we just draw our uh, resistive symbol, then we have a certain highly resistive middle part, and we have a small resistance and also small resistance. That is the situation in here, and here we have one contact typically called as a source and another contact typically called as drain. This is the case. Well, in this case, if we apply certain voltage difference between source and drain, so this is called as VDS. In this course, when I say some how can I say voltage notation with two terminals, actually it is by definition, it means that the difference between VD referred to VS. So usually source is regarded as a reference terminal, then you understand this is 0. Then actually VDS sometimes represents just applied drain voltage in this case, in this MOSFET case. And well, for example, let's say that I have applied 0.7 volt to here. Then what will happen? Now we have a 0 volt here, and here we have a 0.7 volt, and depending on its resistance, there will be current conduction. Since this is highly biased, then we will have a certain voltage, so I. Then how I is determined? I is determined by what? This one? No. This one? No. Only determined by this one. If this largest, only because they are serially connected, if this center resistance is quite high, then you will find that current is quite close to 0. No current conduction. But let's think about another case. If we can control the magnitude of this resistance by some way, so let's say that now we have more or less comparable resistance for this central part, then what will happen? In this case, our resistance cannot be close to 0, and we will have a certain current conduction. As you know, this is the central idea of our transistor. So we wanted to have the current conduction between these two terminals. These two terminals means that source and drain. We wanted to utilize this drain current. However, this drain current is controlled not by drain voltage, not by source voltage, but the change of a central resistance. Then how can we change this central resistance? That is the role of our gate terminal. So here we assume that by controlling or by changing our gate voltage, then we can change the value of our resistance in the central region, sometimes called as channel. Okay, so I make a quite a short description about the operational principle. And do you have any question? So it is really okay to give me any question about these contents. So since all of you have a different, what can I say, background of academic background, so you are quite encouraged to give me any question. Okay. So okay, then let me just go to the next part. Then the point is controlling this resistance. Oh, and you know that this control is done by our gate voltage. By applying certain gate voltage, we wanted to change the conductivity, or in other words, resistivity of this channel region. Then how can we change that conductivity here? And here we can easily understand this one. We are now talking about resistance or conductivity. So this is resistivity and this is conductivity, and they are in an inversion relation. So rho is just the inverse of conductivity. Then conductivity has two proportional factors. Why is it? That is, there are two things. One is number of electrons, and another one is mobility of electrons. These are two factors that determine the conductivity. You know, this quantity is called as mobility, and this is a quite important quantity. So actually, as an engineer, the improving the electron mobility is one of the most important job to improve the performance of your transistor. But you know, the mobility of course changes. Sometimes if you have quite pure material, pure silicon, then maybe your, oh sorry, so I have to eliminate the last one. So your mobility would be, if you have really pure intrinsic material, silicon material, then your mobility will be like this. And in reality, if you make certain transistor, your mobility will drop like just orders of 10 square centimeter or second. So already you have more or less 100 times difference in mobility. Okay, and if you go to polysilicon, or sometimes if you go to amorphous silicon case, then your mobility can be even lower, orders of just 1 or 0.1, 0.01. That is possible. However, please understand, if we just consider silicon, crystalline silicon case, then change of mobility is just at least 2 orders of magnitude. And do you want to have control your resistance just 100 times? I mean that previously your conductivity was sigma 0 when it was lowly conductive, and now you have, wow, 100 times more conductive channel. Oh, then what will happen? In this case, maybe your current will change by a factor of 100. So do you like it or you don't like it? Actually, what we have achieved in these days is the, how can I say, the difference between the most current we can conduct and the least current we can conduct is more or less a billion times difference. So this 100 times difference is not sufficient to our engineering performance. So it means that I wanted to control the conductivity in the channel region, the region between this source region and drain region. At the same time, the region underneath this gate region, so surrounded by source, drain, and covered by this gate, it is not sufficient to modulate our mobility. Mobility does not change much, not in exponentially or logarithmic, so orders of magnitude. Over course, it has a certain change, but it is not that much sufficient for our purpose. Then, what is our choice? The next choice is yes, the number of electrons. Then number of electrons, can you change the number of electrons 10 to the 9 times? The answer is yes. The number of electrons in this system can be changed more than 10 to the 9 times. Actually, usually you can change it more than 10 to the 9, 10 to the 10, 10 to the 11. Such kind of huge difference can be made. So what I want to say is, although our goal is control the resistivity or conductivity of this channel region, actually the change of conductivity can be converted into just the change of electron, because that is huge and that is just marginal. Okay, so are you with me? So still, if you have any question, then it is more than welcome. Then let's go to the next slide. I think that maybe this slide just shows the thing I have explained up to now. So usually we have the bias condition for MOSFET. So source voltage is regarded as a reference one, and this one is applied voltage. So we make certain excitation using the drain terminal, and when we have an electron between source and drain regions, so here we have tons of electrons, yes, and here we have tons of electrons. That doesn't matter. However, in between, actually we have almost no electron, but if we have an electron that can contribute to our current conduction, so this electron is important. Many electrons in this region, they are not much important for our carrier transport. So we wanted to control the number of electrons. Now the key is to control the number of electrons. However, mobility is also very important. However, this is secondary importance. Okay. Now I assume that all of you understand this interesting concept. Then now the next goal is, okay, then I wanted to control or change the number of electrons. How can you do that? In this structure called MOSFET. So it is quite easy to understand. If we change the voltage at this gate terminal, and here we have a metal actually, and here we have a very thin, extremely thin silicon dioxide. Actually nowadays this is not purely silicon dioxide, actually the some mixture of silicon dioxide and hafnium oxide. More or less nowadays, hafnium oxide has a larger volume. But anyway, here we have a very good and thin insulator separating this silicon part and metallic part. Yes. So it means that we have two thin metal semiconductor, and they are only separated by very thin layer. That is current situation. And everybody understand, I wanted to change the number of electrons here, and by applying certain gate voltage, I wanted to control the number of electrons. So maybe typically you learn like this. If we have larger or higher gate voltage, then in this system we have more electrons. Yes. And if we have lower gate voltage, then we have less electrons. True? So that is the way we have learned up to now. But point is, it is true that if we have higher voltage, then we have relatively positive, more positive charges accumulated in this metallic part, and more negatively charged in this semiconductor part. That is true. For example, if we applied 0.7 volt, and instead of 0.7 volt, when I increase the voltage to 0.8 volt, then we will have more positive charges and more negative charges in these two parts. So now the increase of this negative charge is interpreted as increase of your electrons. So are you with me? Any question? So since there is two parts, metal and semiconductor, and in between insulator, and when we apply higher and higher voltage to this metallic part, then anyhow we will have an increase of negative charges in this semiconductor part, and that is negative charge, and that is increase of electrons. But what I want to say is, number of electrons in this MOS system is not necessarily equal to the number of negatively charged particles. That is key point I want to deliver in today's lecture. Okay, it's true that MOS system, and say that previously you have VG. Okay, good. And now you applied additional gate voltage. Then what will happen? Then you will have additional positive charges and additional negative charges in this system. However, these negatively charged charges, one, is not only from electrons. There is another mechanisms in this system. That is key point. Let me just go to the next one. Okay, here we have something like this. This figure is not very easy to understand at a first glance, but let me just introduce this one. What I want to say is, here now we have a MOS system, MOS, and now we have negative charges, and the very first thought is, these negatively charged particles are originated only from electrons. So simply, if we apply higher gate voltage, then the number of negatively charged particles will be increased. Also, the number of electrons will be increased. That is a typical thought. However, we have another second mechanism to provide our negatively charged particle inside this silicon part. What is it? This is depletion. So using the depletion, we can make another negative charge. So let me explain it a little bit more. So you know, this part, when we come back to our previous lecture contents here, that is doped with p-type impurities. Okay, so this is p-type impurities. So p-type impurities means that the atoms are negatively charged. Instead of that, they provide some holes in this silicon crystal structure. So when we have this system can be regarded as what? So here we have negatively charged atomic cores, and there are holes in without this upper part, oxide and metal. However, if these holes are eliminated from this surface area, then what will happen? Previously, without this upper part, the number of negatively charged atoms and holes are balanced. So they are in charge neutral state. However, if we eliminate these holes, then what will happen? What will happen to this the net charge density? Then you will have only negatively charged particles due to not electrons but ionized p-type dopant. So here we have ionized p-type dopant. So if you understand this concept, then now if we have increase of a negatively charged particle, then it does not necessarily mean that increase of electrons. If this mechanism is more active, then electron number is not increasing significantly, and only the increase of this depletion charge or number of ionized p-type dopants will be dominant. So now let's have a look at this graph for now. This graph, we have an x-axis. X-axis is gate voltage. So x-axis is gate voltage. And what we can expect is, since this is a gate voltage, when we have higher gate voltage from 1 to 2 volt, then we will have more negatively charged in this silicon part. And this red curve just shows that behavior. Can you read it? When you have this red curve from 0 volt, 1 volt, 2 volt, how does it look like? Your charges in this silicon part becomes more negatively changing. Okay. However, when we decompose these increase in this part, please have a look at this. Red color curve is decomposed into two parts. One is green and one is blue. So I took just the absolute value of those ones. So that's the reason why they are inverted. But point is, this green one is corresponding to electronic contribution, and this blue one is corresponding to the contribution from ionized p-type dopant. So please try to read this one. From 1 volt, gate voltage of 1 volt to 2 volt, what is the dominant factor of your negative charge or increased negative charge? In this case, you can certainly say that, oh, these green lines changed quite much. However, this blue line does not change much. So from 1 volt to 2 volt, in this case, increase of a negatively charged particle is more or less solely determined by electrons. This is quite a desirable state. When we change gate voltage, the number of electrons are changed accordingly. So are you with me? But another point is, please try to read the range from 0 volt to 1 volt. Even in this case, our negatively charged particles changed from here to there. There are more additional negatively charged particles in this range. But when you have a look at this one, here to here, in this case, we have a certain increase of electrons, but also we have a certain increase of what? Certain increase of depletion charge. Means that the number of p-type dopants are, the ionized p-type dopants are increasing in this range. And if we go to another range here, from -1 volt to 0 volt, then things are almost completely different. In this case, electron doesn't change at all. And only change of this red curve is solely originated from what? From the extension of a depletion layer. So what I wanted to say is, it's quite simple. My main message is quite simple. In this MOS system, the number of negatively charged particles obtained by applying additional gate voltage is not always equal to the change of electrons. There are two competing mechanisms, and depending on gate voltage, you have a different behavior. Qualitatively, you can say like this. When you have a relatively low gate voltage, then dominant mechanism is depletion. So in this case, you have not many electrons inside your system. And if you go to sufficiently high gate voltage, then now the mechanism to supply additional negatively charged particle now becomes electrons. Okay, so this MOS system, we have two different competing mechanisms, and depending on gate voltage, they behave quite differently. This is the key. So maybe some of you say that, oh, why that is so important? Why the professor stressed this quite seemingly quite obvious thing again and again? The reason is like this. If we have perfect capacitor, then we don't have switch. Please note that the goal of our work, entire work in this CMOS field is to make a switch. Then switch has two phases. One phase is on phase and another phase is off phase. Important one is on is not that difficult, but point is off is difficult to have. since we have the second mechanism called depletion, now we can have a certain voltage range where although we change gate voltage, there is no change in the electron density. That is key point. Let's say that if we have such kind of thing, electron changes just linearly over gate voltage, then what will happen? Even when we apply zero gate voltage to our system to turn off our transistor, if we have a slight change in our gate voltage, then conductivity will change accordingly. That is not a desirable situation. When you shut it down, it should be completely isolated. However, if we have this kind of behavior, then noisy gate voltage will introduce also fluctuation of your conductivity. That is not acceptable for our situation. Okay, so I think that this is the main message, and this is the key point of MOS system. Inside this MOS, we have two mechanisms. So when we have a sufficiently low gate bias, although we change gate voltage, we cannot get certain electrons. And when we have a sufficiently high gate voltage, now dominant mechanism becomes the electron generation or electron inversion, and that gives us our application field. So here we have a certain knee point or transition point between the depletion dominant behavior and another one is inversion dominant behavior. And this knee point is called as threshold voltage. So now when you have the voltage lower than threshold voltage, then actually you can say that we have almost no electrons at all. And over the threshold voltage, now you can understand the increase of electron is just follow piecewise linear function. So simply speaking, we can say that in this way. We can introduce a piecewise linear function like number of electrons, n is just 0 when your gate voltage is below threshold voltage. So you are now just describing this behavior. And beyond gate voltage, beyond threshold voltage, then your electron density will just follow linearly proportional to the difference between Vg minus Vth. And when you have just Vt, then you will have 0, and after that there will be increase. Of course, this is electron density and this is voltage, so they are two different quantities. Of course, we have a certain proportional coefficient, but that will be discussed later. So are you with me? So simply speaking, I want to say that this is the essential of a MOS system. We are now talking about, up to now, we have talked about what? The vertical structure. The vertical structure to determine or to control the number of electrons in this part. So simply by applying certain gate voltage, we can control the number of electrons. So when we have a sufficiently high gate voltage, then we have many electrons and considerably high density of electrons, and they will conduct electrons. And if we have sufficiently low electron density, then unfortunately we have almost no electrons in this channel region, and source and drain are electrically isolated, and we have completely no current conduction. So that is the beauty of this operation of MOS. Okay, so I think that although we have just discussed in a qualitative way, we will revisit this concept as the lecture progresses. So yes, and now we are talking about body. Body, or sometimes called as a substrate, and this is another one, another terminal. So source and drain and gate are all covered, and body is not explained up to now. Where can you find body? Here, typically we say in this way, but this is just a schematic one. Actual body is not located in this, how can I say, bottom of your wafer. You know, this is once again, how thick was it? So about 600 micrometer. So this is not actual position. Actual position of your body contact is like this. Here we have a p-type substrate, and p-type substrate is of course much more extended here. And here we have introduced highly doped p-type resin, and here we have another metallic contact. So that is connected to the ground. So what happens in this case? This ground 0 voltage is copied, and copied. And this is, since this is a p-type region, this is highly conductive, and since this p-type region and our bulk p-type substrate are connected, so the reference voltage for this p-type region is connected to the ground. So simply speaking, body contact or substrate contact is used to supply the reference voltage for our p-type substrate. Okay, so that is the role of our p-type substrate. But I wanted to say that in these days, the state-of-the-art device is no longer look like this. So state-of-the-art device looks more like this. Here we have once again source and drain, and here we have a certain height of our source and drain region, and here we have drain region, and here we have gate, and the same gate. And actually the gate is just surrounding this central part. So here we have a surrounding gate. So sorry about my ugly drawing, but anyway, what I wanted to say is this is the most advanced device in nowadays, and they are separated by, here we have certain insulating layer. So in this case, since we have no connection here, of course here we have a silicon substrate. However, this silicon substrate is structurally isolated from the channel region. Please note that previously this channel region was structurally connected to the substrate. So in these cases, importance of body terminal is much lower than our previous planar MOSFET. So we will concentrate more or less. We will concentrate on these three parameters or three contacts. And let me just read our slide. So when gate voltage is low, here low means that lower than threshold voltage, then no current flows and transistor is turned off. And yes, and again, when the gate to source voltage, the difference between gate and source is high enough. High means that higher than threshold voltage, then current can flow. And when when this case, when you have this case, we say that transistor is turned on. That is quite simple. And let me go to my maybe the second final slide. Um, Up to now, I have talked about N MOSFETs. Always I saw that, I told you that there is electrons and number of electrons are important or something like that. But here we have another device called P MOSFET. So P here means that positive of course, and positive, and N MOSFET, when you say that N MOS, the N represents negative. The name N comes from the polarity of your electrons. Electron carries negative charges, so this device is N MOSFET. So since we have P MOSFET, so you can easily understand in this case, charge carrier is no longer an electron, but a hole. Here we have a hole dominant device. Then in this P MOSFET, now you collect holes. Number of holes are controlled by your gate voltage. So otherwise everything is identical. So previously when we have N MOSFET, when we have a sufficiently high voltage, then we will get many electrons. And now in this P-type MOSFET, P MOSFET, when we have a sufficiently low voltage, then we will have sufficiently high number of holes. So are you with me? So simply speaking, let me just compare these two devices. Here we have an N MOSFET, and here we have P MOSFET. P MOSFET is usually drawn with a bubble, and when we have high gate bias, and let's say that we have applied the same high gate bias, then let me just try to see what happens. In this case, we will have many electrons because we have collected electrons beyond the depletion charge, and in this case for same gate bias, in this case no holes at all, nothing. So in this case, for this P MOSFET, is it conductive or resistive between its source and drain? In this case, it becomes highly resistive. However, for the same gate bias, in this N MOSFET, the current path between drain and source becomes highly conductive. Okay, so then let me just make a certain table. High. Then N MOSFET and P MOSFET. This N MOSFET becomes conductive, and this one becomes resistive. Then let me just go to the next one, so you can easily understand. The answer is quite easy. If we have low gate bias, then what will happen? If we have a low gate bias, then yes, we have no electrons at all. so it becomes really resistive. However, for low gate bias, now we have a lot of holes, so inverted here, so we have highly conductive channel. So beauty of this CMOS technology is this existence of a p-type transistor. So to undergraduate students, seemingly the existence of a p-type device seems to be quite natural. However, I wanted to say that other computing technologies do not have p-type or this complementary device. For example, if we talk about 3-5 materials, 3-5, they have quite high electron mobility. They have really superior performance for N-type electron-dominated devices. However, unfortunately, they don't have high hole mobility. Even for some materials, actually, p-type impurity itself does not exist. There are only N-type impurities. So, in the case of silicon, it's quite interesting because silicon's electron mobility and hole mobilities, of course, electron mobilities are somewhat higher. However, they are really comparable. I want to say that the maximum value we can expect for electron is like this, and about 500, that is the maximum value we can expect for holes. Of course, this is just the maximum value. So what you can say is there is more or less 3 times difference in electron mobility and hole mobility. Oh, 3 times is huge. But you know that if we go to other materials, the difference is not just a factor of 3. 10, 100 times difference can be easily found in many materials. Okay, so another one is silicon has both N-type dopant and P-type dopant, and we can use both of them quite easily. However, unfortunately, for other materials, it is typically difficult to find P-type dopant. So, I don't know why silicon has such kind of desirable properties, but who knows? But anyway, fortunately, since silicon has a balanced behavior between its holes and electrons, and p-type substrate, p-type dopants are available, that is the reason why we can have CMOS technology. CMOS means that here C is complementary, means that at the same technology we can provide both of N-type and P-type material, or N-type and P-type devices at the same time. At the beginning of MOS technology, actually there was either N-type transistor or P-type transistor. For example, the very first microprocessor was made of only P-type transistor only. And there was many N-type only technologies. And later on, now technology becomes more and more mature. Then now we have a CMOS technology. So I wanted to say that don't underestimate importance of this P-type material or P-type device. The existence of P-type device really makes the CMOS technology as a king of semiconductor device technology. That is really critical point we have to understand. Okay. Of course, it's true that P-type, typically P-type device is not as powerful as the N-type device. So that is true. But anyway, it's much better than nothing. And okay, so now we have just 7 minutes left, so I will just quickly cover this one. Today, I told you that I applied 0.7 volt to the drain and sometimes also apply 0.7 volt to the gate. So typically, this value, the voltage value applied to the gate or drain, is called as a VDD. So this is the maximum value we can apply to our transistors. However, although in these days this value is really reasonable, and nowadays sometimes we have 0.65 or 0.6, those values are also used, but previously its initial value was not 0.7, its initial value was 5 volt. So 80s, 90s, that was the value of 5 volt. However, as time elapsed, then people found that, okay, in order to keep our technology evolve, then we have to reduce the VDD values. So this is 0.065 micrometer, and this is 65 nanometer technology. This is a really somewhat old technology, but here we have around 1 volt. And where are we now? When we draw in this scale, then we are living in the era of 0.003. And here we have values about 0.7 volt. Oh, there was a rapid decrease, and nowadays this value is more or less saturated, but still engineers want to reduce this value. The goal is, maybe if we can achieve the operational voltage lower than 0.5 volt, that would be quite beneficial for low power applications. So that is the thing. And now we are living in the era of 0.7 volt. Why we scale down in this way? That will be explained later. So finally, in this course, we are talking about digital circuit. So in this digital scene, transistors are used as switches. So now we can summarize in this way. And MOSFET, as you know, when we apply high gate bias voltage, then it becomes quite conductive. So now drain and source are electrically connected. So simply speaking, when we have a sufficiently high voltage like VDD, then drain and source are electrically connected, and we are saying that the transistor is on or switch is on. And on the other hand, when gate bias voltage is 0 volt, then they are isolated, so source and drain, and we say that switch off. But in the case of a PMOSFET, fortunately, we have the opposite possibility. So when we have 0 volt, the switch is on, and when we have VDD to our gate voltage, then transistor is shut down and switch is turned off. So we have two opposite behavior of two different transistors, and we will use these properties to build our logical operations. Okay, so I think that we have only 2 minutes left, and if you have any question in today's lecture, please feel free to give me any question, or even after this session is over, you are quite welcome to give me any question. Okay, so then if you don't have any question, as you wrap up today's lecture. And this Thursday, please directly come to this lecture room so I will give you a second lecture. Okay, thank you for your attention. Bye.